Hi, I'm Brad McCoy. Welcome to It's a Great Day for Gauss-Bonnet Video 1. In this video, we're going to prove a special case of the Gauss-Bonnet theorem, sometimes called the theorem of turning tangents. You may have seen this before. It's pretty basic, but that doesn't mean it's not powerful. We're going to use this result to prove Pick's theorem, a nice theorem in discrete geometry. Hopefully, this video is accessible to almost everyone, so enjoy. This is our first video, so I welcome constructive feedback. You could leave it in the comments or direct message me. We want these videos to be as fun and as interesting as possible. And so we have many great days with the Gauss-Bonnet theorem. All right, let's jump right in. Okay, so it's a great day for Gauss-Bonnet, certainly here. We're in Bozeman, Montana, so here's video 1. So as mentioned in the preamble there, we're going to talk about the theorem of turning tangents, and we'll say this is a special case of Gauss-Bonnet. And then we'll use that to prove Pick's theorem, okay? This work is heavily influenced by Yuri Matuszak's book, Using the Borsuk-Ulam Theorem. And in that book, a borsuk is a badger, and they use the badger as their end of proof symbol. So here there's a thing called a bonnet macaw, and we're going to use this little sketch I made of this bonnet macaw as our end of proof symbol as a sort of fun reference to that book. Okay, so let's consider simple polygons, and we're in the plane. Let's say in the plane. That'll be important later. So let's call this, here's our polygon P. And what we're going to do is we're going to traverse P starting at some point, and we're going to record how much a tangent vector spins around as we go the whole way around back to where we started. So I'm going to use my little lasso here. So we'll start here, not spinning at all on an edge, but when we get to a vertex, what happens? Well, we see two angles appear, and we'll call this beta 1. And we'll estimate that to be approximately 2 pi over 3. And we'll call this an exterior angle. So we'll say beta I are exterior angles. And then we'll say the complementary angle is alpha 1 is interior because it's inside the polygon. Okay, and we'll continue around P here. So picking up where we left off. We'll get to this point and we'll estimate beta 2 to be approximately, what should we say, how about pi over 4? And onward we'll get beta 3. Let's say this is also approximately 2 pi over 3. And now at beta 4, something interesting happens. What's happening? Well, we got to turn to the right this time. So we're going to say our beta 4 is a negative pi over 4. So we're going to adopt this sign convention. So a left turn is positive and a right turn is negative. So we've made a negative pi over 4 turn there. And then to bring it home, we'll get the beta 5 and we'll estimate that to also be approximately 2 pi over 3. So we're interested in the total amount that our tangent vector spun around here, including this sign convention. So the sum of our beta i's, I equal 1 to 5 in this case, is going to be 2 pi over 3 plus pi over 4 plus 2 pi over 3 minus pi over 4 plus 2 pi over 3. We'll see that our pi over 4's cancel, and we're left with 2 pi. And maybe this is not surprising to you. Why not? Well, we have to make one complete revolution when we traverse our polygon. So we're going to do our tangent vector spins around to the left one time. So that gives us a total sum of these exterior angles is going to be 2 pi. So that's our theorem of turning tangents, or a special case of the Gauss-Bonnet theorem. So let's highlight that with our big idea. So our tangent vector makes one revolution when we traverse P. And this is sort of obvious, but also pretty cool. So we'll emphasize that as our big idea. And notice, like, it doesn't matter what the polygon looks like. We could have somehow some crazy polygon. Well, all our edges have to be straight, so let me be a little bit more careful. And if we were to make some sort of dent in our polygon, we have this conservation happening, which is somehow also interesting. So maybe I put a little dent in here. What do we notice? Well, here we're going to make, we're turning to the left, so this is a positive pi over 4. And then this will be, we're turning to the right, so a negative pi over 4, another negative pi over 4, and then a positive pi over 4. So things didn't change. We just, even if we put a little dent in here, yes, we created more turning to the left, but we also created more turning to the right. So as a net, the total amount of turning we did hasn't changed. Okay, so this is our theorem of turning tangents. Let P be a simple polygon in the plane. Again, I'm going to emphasize in the plane. That'll become clear in later videos. We have n vertices and exterior angles, beta 1 through beta n, interior angles, alpha 1 through alpha n. Then 1, the sum of the exterior angles is 2 pi. And the sum of the interior angles is pi times quantity n minus 2. So let's talk about a proof of this. So as we discussed above, the proof of 1 will be because of our big idea. We're making one complete revolution. And then for the proof of 2, it comes from the fact that our beta i's and alpha i's are complementary. So beta I plus alpha I equals pi. So when we consider our sum of our alpha i's, we can rewrite this in terms of our beta i's, namely pi minus beta I. And then we can distribute our sum and use 1 that we know the sum of the beta i's. So we'll get what? Just pi added up n times will give us n pi minus 2 pi. So this will be pi times n minus 2 as desired. So let's put our Bonnet macaw here as our end of proof symbol. Okay, so theorem of turning tangents. Again, we'll call this special case of Gauss-Bonnet. P is a polygon in the plane, n vertices. The sum of the exterior angles is 2 pi, and the sum of the interior angles is pi times quantity n minus 2. So maybe you remember that from your geometry class at some point in your life. So pretty cool. No matter what our polygon looks like, these values or these sums will always hold true. Okay, so let's use this to prove Pick's theorem. So here we have our polygon with vertices on the Z2 lattice. So P has vertices on Z2 lattice. Let's make that a 2. What that means is at every integer coordinate we have that's where one of our vertices has to be. And Pick's theorem gives us a convenient way to calculate the area of one of these polygons. So if we say I is the number of interior lattice points, and B is the number of boundary lattice points, then we can say our area of our polygon is I plus B over 2 minus 1. So that's Pick's theorem. So this is Pick's theorem. So let's calculate this for our example. So how many interior lattice points do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So I equals 8. And how many boundary lattice points do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll get 11. So our area by Pick's theorem should be 8 plus 11 over 2 minus 1, which is, what is that? 12.5. So maybe you're paranoid like me. You could say, I don't know if I believe Pick's theorem. Well, you always have the option to chop this up into triangles and rectangles. So if we do that, what's the area of this one? 1/2 base times height. So this is 2. This would be area 1. This would be, this triangle would be a half. And we'll have 1, 2, 3, 1, 2, 3. So the area would be 9. And we get 12.5 again. So notice Pick's theorem made this computation easier. I didn't have to do this surgery into rectangles and triangles. I could just count these lattice points. Okay, so let's talk about a proof of Pick's theorem. This is such a slick proof. It's originally due to Blatter in 97, and then restated by Tabachenikov in 2014. Let's make sure we say that right. And this proof is in his paper called Proofs Not from the Book, making the argument that this should be like the best proof of Pick's theorem, which is sort of nice. Okay, so here's the idea. At each lattice point, we're going to put a unit ice cube, and then we're going to apply some heat to these ice cubes and melt them. And we're going to look at how much, so we'll have a water covering the plane, and the first thing to observe is the amount of water inside the polygon is equal to the area. So we have a unit volume of water for each unit of area in the plane. So hopefully you can convince yourself that the amount of water inside P is equal to the area. The next thing to observe is the amount of water that crosses an edge is equal in both directions. So how do we want to say this? Total amount of water that crosses an edge is 0. So yes, some water will cross an edge. So for example, this cube, some water will flow into our polygon, but there's always a symmetric lattice point inside, and an equal amount of water will flow out. So the total amount that crosses an edge is 0. And then if we have a vertex that's on the interior of an edge, half is going to come in and half is going to come out. So the total amount that crosses an edge is 0, which is nice. Okay, so let's make this precise. So let's say B prime is a vertex that's in the interior of an edge. And let's say that N is a vertex of our polygon. Or we have N vertices on our polygon. So maybe number of these, and this is number of vertices of P. Okay, so by the first bullet point, by the second bullet point, if you're an interior vertex, all that water is going to stay inside P. So I water inside. If you're in B prime, well, we're going to get half the water inside. So half the water inside. And what's left to consider is these N vertices of our polygon. So here's where we're going to use our special case of the Gauss-Bonnet theorem. So if we consider a vertex, well, how much water is going to end up inside of our polygon? Well, it's exactly the interior angle over 2 pi. So interior angle over 2 pi. So if we consider the sum of all of our interior angles, how much water are we going to contribute? Well, we can factor out our 1 over 2 pi and get our sum of our interior angles. And we know by special case of Gauss-Bonnet that this is pi times n minus 2. So this is by Gauss-Bonnet. And we're left with our pi's will cancel, and we'll get n over 2 minus 1. So combining these last 3 bullet points, we'll get our area is equal to the number of interior lattice points, because all that water stays inside, plus our edge vertices over 2, plus our corner vertices over 2 minus 1. So that's just all of our boundary vertices minus 1. And we get Pick's theorem. Okay, so let's put our macaw in here as our end of proof symbol. Okay, so what did we do in this video? We looked at a special case of the Gauss-Bonnet theorem for polygons in the plane. And we came up with formulas for the sum of the interior and exterior angles, and we used that to prove Pick's theorem. So next time, what are we going to do? We're going to state a more general version of the Gauss-Bonnet. And then we're going to talk about what are some of the symbols that appear in there. So we'll define curvature, geodesic curvature, Euler characteristic, that sort of thing. So thanks for tuning in. And